Good afternoon. I appreciate your taking time to attend this webinar. The principal audience for this is people who already have some familiarity with our product, Syndeia. My objective is to show the new features introduced in Release 3.1, and I also want to offer some insight into where Syndeia is going. 3.1 is one step in making Syndeia a robust, scalable enterprise application for model-based systems engineering, or MBSE. However, I also realize that some of you are less familiar with MBSE, not to mention Syndeia, and for these people, I will give a brief overview. Intercax started as a commercial spin-off from the Georgia Institute of Technology, and our main office is still located a few miles north of Georgia Tech in Atlanta. We also have a development office in Pune, India. Our focus, really our only business, is helping organizations adopt best practices in model-based systems engineering. We do this primarily through developing software, both custom and standard. Our main product is Syndeia, from the Greek root for the practice of bringing things together. It's an integration platform for connecting engineering models and a variety of tools. We also offer products for connecting models with simulation using SysML parametrics. And we do some MBSE training and consulting, often in collaboration with Georgia Tech. Our customer base is heavily aerospace, defense, and automotive, but we have also worked with companies in energy, healthcare, consumer products, and other fields. I want to start by describing what we mean by model-based systems engineering and MBE, model-based engineering, and how Syndeia helps realize those concepts. For Intercax, the core feature of MBSE is the idea of using a single, unified digital model to describe a system, where structural components, behaviors, and requirements are connected in a multidimensional network. We can project the contents of this model in the right framework to generate all the views and all the documents that we still need to develop the system. And we know that these views will be consistent because they're generated from a single source. And when the model changes, we can generate a new set of documents with a few clicks of the mouse. If we can do this, we get to spend a lot more time on engineering and less time in document management. That's the vision. The reality is that engineering organizations use a lot of different software tools, usually from multiple vendors. Some of these tools, like architecture modeling, requirements, and simulation, are typically concerns of systems engineering. Others, like PLM, ALM, and CAD, not so much. But information about the system is distributed over all of these tools and repositories. The challenge, then, is how do we build a single unified system model, call it the total system model, that extends over all of them? Because it goes beyond the traditional domain of SE, we and others call this idea model-based engineering, MBE. One approach is to build a network of connections between model elements in different models and different tools. This kind of model of nodes and edges is called a graph, and Syndeia's job is to create and maintain and display such a graph. Now, Syndeia began with a specific architecture for this graph. At the center is a SysML architectural model, and the elements in this model are connected to elements in all the other engineering models shown around it. Now, SysML models make a good hub. They let structure, behavior, requirements, and analysis all interact on a level playing field. But SysML models shouldn't be the only hub. And we will see later how Syndeia is going beyond this, but this is where Syndeia is today. When we introduced Syndeia in 2014, our first step was making connections from a SysML model in either Magic Draw or IBM Rational Rhapsody to PLM and database tools, specifically Teamcenter, Windchill, MySQL, and Excel. In the second release, we added CAD tools, NX and Creo, and Simulate. Last summer, Syndeia 3.0 broadened the range of domains with GitHub for software configuration management, DoorsNG for requirements, and Jira for project management. In 3.1, our focus today, we will demonstrate the new interfaces to Jama software and Simulink Stateflow. But equally important, changes have taken place under the hood, including the addition of a dedicated back-end server to store the intermodel connections. And we will be talking about the implications of this. Now, when we talk about connecting two tools, it is critical to get specific about use cases. In other words, what do we want Syndeia to do with that connection? Well, that depends, of course, on the tools being connected, and Syndeia supports a lot of different use cases. I want to mention a few of the more important ones for our customers. With connections from SysML to PLM repositories and databases, one use case is to take a SysML block structure from the conceptual design stage and use it to generate a PLM bill of materials for the next stage of system development. And we can also do the opposite. When we're starting the conceptual design for a new product or a second generation of an existing product, we can use the existing product data in a PLM system to generate the building blocks for a new SysML model. In either case, this is not a simple export-import transaction. Syndeia keeps the models connected so that when differences evolve in one or both, Syndeia can compare and update the product info to keep the models consistent. SysML CAD use cases are similar. CAD models contain composition information and assembly models, and dimensional attributes like size, mass, and center of gravity. As the CAD design changes, Syndeia can update those values into the SysML model, for example, to compare against requirements. For those familiar with SysML and Simulink, there are obvious commonalities between a Simulink model and SysML activity and internal block diagrams. Some users start to model the system in SysML and want to push it to Simulink for simulation. Others model initially in Simulink, especially for software development. But we want to move these models into SysML to share with others. Well, when we look at the new Stateflow interface for Simulink shortly, we'll see how that works. Another common pattern is to manage requirements in a requirements management tool like DoorsNG or Jama, but then move them into SysML as needed. When we demonstrate the new Jama interface, we'll see how the compare and update functionality works to keep them consistent. With ALM tools like GitHub, we want to be able to connect a SysML element to a specific version of a software file and see if a later version has been committed. When we link a SysML element to a Jira issue, the system engineer now has access to the latest project management information about that element's status, schedule, and assigned personnel. Finally, the network of connections we have created in these use cases is useful in its own right in providing traceability across the total system model. Now, Syndeia provides several ways to visualize the graph, and we are working with our customers to find the best ways to present this information. We will look at some of that work later. However, before we move on to the demonstrations, I wanted to address a common question. Does Syndeia use open standards? Well, the answer is yes. Syndeia uses a variety of open standards, APIs, and frameworks, starting with OMG SysML, but also including OSLC and RESTful APIs and many others. However, our use of standards is pragmatic. We use them where they are robustly implemented and where they serve the customer use case. Where necessary, we go beyond the standards to things like native tool APIs or even file transfer to meet the customer's needs. Well, this completes the overview. For those who have heard this before, I apologize for the repetition. For those for whom this was too fast, these slides are available on request, and we will post a video of this presentation on our website. But now I want to move on to the demonstration of the Syndeia 3.1 features. Now, I am going to use pre-recorded screen recordings I took over the last couple of days. To save time, and to avoid the usual runtime demo glitches like servers going down or web connectivity slowing down. I want to start by demonstrating the JAMA software interface. We're looking here at a Rhapsody model of a UAV, an unmanned aerial vehicle. It's at a very early stage here, and among other things, it contains no requirements. So our first task is going to be to launch Syndeia from the Rhapsody tool and bring in a set of JAMA requirements. So we're going over to the model on the right side, going down to a menu item Syndeia, launching the dashboard. In the first screen, this is called the Repository Manager, we see a list of connections that we have to repositories and other tools that have already been set up. That is, Syndeia is storing our access credentials, our usernames and passwords and URLs, to be able to access our accounts in these different tools. Now we have, in this particular case, the ability to connect this one SysML model to Doors, GitHub, JAMA, Jira, MySQL, TeamCenter, and Windchill, plus files like CAD files and Simulink files and Excel files in our local file system. But let's move to the Connection Manager now and look at the contents of our JAMA file. We're going to go down and expand this to find a set of UAV requirements that we want to bring into the SysML model. So down here we have something called a set in JAMA. It contains a top-level requirement which has several sub-requirements, and we simply drag it and drop it onto the left-hand side to an empty package in the SysML model. And now we can see, as we expand that particular package on the SysML side, it has all of the different multiple levels of requirements that have been brought over in that single action. If we go back to the SysML model, we can see that that package now contains all of those requirements. We can go ahead and drag one of them into a requirements diagram in SysML because I want to go ahead and I want to start to change things. I'm going to change the contents of a particular performance requirement, endurance, which determines how long the UAV can stay aloft independently. I'm going to take that from 8 hours up to 10 hours. Now I've got a discrepancy between my two models. The requirement says 8 hours in JAMA, but has now been changed to 10 hours in SysML. Syndeia has the ability to compare these models and see where the differences lie. So we're going to do that next. We're going to go to what's called the Connection Browser tab, which allows us to see the individual connections. And we're going to do a comparison. You can do it across individual requirements or across all of the, in this case, we're going to do it across the performance requirements. We're going to go to Compare SysML and Target, and we're going to generate a difference table. Now, if we take a look at this, we can see that there's one red line. That red line represents the difference between the source, that is the SysML model, and the target, that is the JAMA repository, for this particular issue, the text in the endurance requirement. If we hover over it, we can see we have the 10 versus 8 hour limit. We also have the ability now to update. Not only compare, but we have the choice of syncing the SysML model contents to JAMA, if we want to overwrite JAMA, or vice versa, to take the JAMA contents and write them back over to the SysML model. We're going to do the second in this particular case. We're going to sync target, that is JAMA, to SysML. And we can do this again on individual requirements or multiple requirements. And now we can see that it has been changed in the SysML model in Rhapsody back to the original pattern of 8 hours. All right, that was a quick demonstration of the capabilities of the JAMA interface and how Syndeia can do a model transform of requirements from one tool to another, can do a comparison between those linked models, and do an updating between those linked models. Now we want to do something similar with two different tools. We're going to start off with a magic draw state machine diagram and transform that, push that into Simulink Stateflow. So looking at a state machine diagram in Magic Draw, in this case, or specifically Cameo System Modeler, we can see that we have 4 different states, and launching the Syndeia dashboard once again, we go down and we find that state machine model within that state machine, flight states, and we're going to drag that into an empty package on my local file system, which is called One Demo State Flow, and use this model transformation drag and drop operation to be able to take flight states over and drag it into the demo package and confirm that we want to do that. And now we're going to wait for a few moments and see that ultimately on the left side here, we have created a Simulink model called flight states. And as we go ahead and expand that it contains a state flow symbol, which contains the state machine and the various states and transitions. So that's now been created on the Simulink side. Now we could launch MATLAB and Simulink and state flow as normal to look at that, but we also have the capability with Syndeia to be able to go to the SysML element that's linked to that model and open MATLAB from there and launch that model from there. And so that's what we're going to do. We've gone down to that flight states on the left-hand side of the dashboard, and we're going to go down to Open Connected Artifacts. And this will allow us to launch MATLAB from the Magic Draw Syndeia interface and go directly to that particular model. So again, we launch MATLAB, we call up the specific model of interest, and there's the flight states symbol. If we double click on that, we'll open that. And we can see here are the states and transitions that have been transferred over from the SysML model. And we'll fast forward and rearrange the various transitions from the default layout condition to be able to show how the patterns of the transitions are the same and the states are the same as in the original SysML model. Now, once again, the difficulty over time is that one or both of these models is likely to change. We need to be able to recognize those changes, and then we need to be able to reconcile them. So in this particular case, we're going to modify the SysML model again. We've recognized a problem with our control logic. This idea of an autonomous landing occurs when we've lost communication and we want the UAV to return to base on its own. But what happens when communication becomes restored as we do that? Now currently, in the original model, it simply says that we go right back into the manual flight mode. But it doesn't require a confirmation from the ground station that we have an operator ready to resume control. So we want to put that logic into it. That's going to mean creating a new state. We'll call that pending. And we're going to change the transitions so that this outgoing transition from autonomous landing is transferred to pending. The incoming transition into manual flight is what puts us into the pending, but we'll add a new transition from pending back to manual flight, which will ultimately be triggered by some kind of a confirmation signal from the ground station. Now we've made all of those changes to the SysML model, but again, the Simulink model side has not been changed. So that's what Syndeia will do. We will find that same connection to the flight states. And first of all, we will simply look for the changes, the differences, by doing a comparison between the models. And that brings us up to the difference table again. Now it turns out here there's changes in both the states because we've added a new state, and in the transitions. When we moved the destination or target of a transition, we have essentially done a deletion of one transition and the creation of a new one. So in this particular case, we've got one new state pending on the SysML side that we don't see on the target side, and we've got 2 deleted transitions and 3 new transitions on the SysML side that don't match up with the Simulink Stateflow model. So again, we can do an update here. We can sync SysML to target. And if we return to the state flow model and open it up, we can see that the new states, including the pending state at the bottom, and the new transitions have been created in the state flow model automatically. Again, we'll fast forward through some of the rearrangement of the states and the transitions and see that the new model of the state machine, again, corresponds with the old one. Again, it's worth noting that in its current form, the state flow interface from Syndeia only matches up the common elements of states and transitions. Other features of the SysML model or the state flow model, like triggers, guards, and effects for the transitions or internal behaviors for the states, are not being transformed and compared and updated currently. That may happen in the future. Now, Syndeia 3.1 has some other useful new features. Model synchronization is now part of the Simulink interface as well as state flow, and the latest versions of MATLAB now provide API access that makes model generation, comparison, and updating much faster than before for this interface. Syndeia also now exposes Windchill projects and libraries as well as products. And finally, the ability to search the Syndeia connection database is greatly improved. This last one is an aspect of adding a dedicated back-end database, as I mentioned earlier. In Syndeia 3.0 and earlier, Syndeia stored the inter-model connections between models and different tools in the SysML model itself. This was not especially scalable. It presented some problems in user access and control, and it also ruled out much of the power of modern database technology, especially graph database technology, to be able to search, filter, and query the connections. In Syndeia 3.1, we give the users the option to store these connections in a separate Cassandra database, which relieves a lot of these limitations. We also offer a second connection to a Neo4j graph database as a prototype feature to let users begin to explore the power of this graph database approach. We want to be able to trace connections all across the total system model, using both connections between tools and connections inside tools to let us see where our data lives. Now, in this prototype feature, we export the Syndeia-managed intermodel connections and the SysML intramodel connections, the relationships like associations and dependencies, together into a Neo4j Community Edition database, which users can download and install for free to test. Let's go back to the video, and we'll go to another Magic Draw UAV model, but one much farther along, where we've created a lot of different connections to different tools. Now again, we can launch Syndeia, but in this case we're going to go down to a utility called SysML to Graph that does the export to a Neo4j graph database. Now this is the web interface for that graph database. And again, this is available to download for free for your evaluation. And at the top line, we have the command line where we can post the queries to the contents of that database. And the first query that we're going to do is simply to show us everything, to show us all the nodes and all the edges. And that gives us what is really kind of a hard to interpret diagram. In this case, there's over 1,200 different nodes and a larger number of requirements. So while this gives us a sense of the contents of the database, this particular query is not terribly useful unless we simply want a text dump of everything. But we can begin to be more specialized, more narrow in our queries. And let's go to a second one that we've staged up here, which is to show us every JIRA issue and what it is connected to. We're using what's called the Cipher query language here at the top. And so when we go ahead and we run this particular query on the database, we get a somewhat more manageable diagram. In this particular case, the yellow nodes happen to be SysML activities from the Magic Draw model, and the gray nodes are JIRA issues from the JIRA repository. And we see two different types of connections here. From the yellow node to the gray node, we see what are essentially intermodal connections, reference connections between the SysML activity and the JIRA issue. So from each of those activities, we would be able to go directly to the JIRA web interface, assuming that we have access to that repository. Between the yellow nodes themselves, we have what are essentially get behavior relationships. In other words, a decomposition of the central top-level activity here into sub-activities and sub-sub-activities. If we zoom out, we can see that particular pattern is that the SysML elements, the intra-model connections, are shown between the yellow nodes. So we have a way of connecting both across intramodel and intermodel connections and displaying those and finding those in a single query. And we can use these for a lot of different types of query applications. For example, we can say, here's a particular JAMA requirement, endurance. I want to see every SysML element, every SysML block, in this case, the aircraft platform block, which is connected to that JAMA requirement. In this case, the connection is indirect. The aircraft platform block is connected to a SysML requirement, which is then connected to its corresponding JAMA requirement. Now, in a case like this, sometimes we need to be a little broader. We're interested not only in the directly connected block, but in every other block that uses that, because they would be impacted by a change in the JAMA requirement as well. So in this case, we're going to look for that block and for the blocks that own that block. So again, a slightly different query. We've expanded it. And the result shows now that we have a JAMA requirement for search capability connected to a SysML element, which is satisfied by the flight software block, which is owned by the software block, which is owned for the CUAV block. And we can look at it from the opposite point of view. We can take apart and ask what elements, what requirements affect this. The aircraft platform block, for example. We can see that it or its part properties, like powertrain or rotor, are connected to SysML requirements. And we can see exactly what connections occur. Or we can again go beyond that and look not just for its parts, but its parts, and go farther down the chain. And we see that now we have even more nodes, more blocks in purple, more SysML requirements in green, more JAMA requirements in gray that have been identified. As the number of different elements expands, we can also go to a tabular view of this to be able to look at the contents of this. In this particular case, we have a lot of different rows in the table, and each of those rows gives us the start, the definition. Finally, here we see these are the various JAMA requirements that are connected and affect the aircraft platform through at least two levels of part property association. We can also start to talk about requests that no longer are concerned with SysML elements, but this is a query that says, tell me all of the GitHub file commits that are affected by that JAMA search requirement. So in this particular case, it turns out there is one. We run the query, and we will see that there is a specific GitHub commit requirement, the one identified there, which is linked back to the JAMA requirement through multiple connections running across both intermodel and intramodel traces. We can even begin to ask such simple questions as, is one element connected to another element? And if so, how? And so this last example will do that. It says we have an aircraft block called aircraft platform, and we have a windshield part called battery. Are they connected? And the tabular result says, yes, they are. And it turns out that it's an indirect connection through multiple connection points. Hopefully at this point, we can begin to show you how This ability to create a database of connections, both inside models and between models, gives us the ability to see connections, to find non-obvious extended connections across the entire total system model. Now, this feature is probably not the final form of our solution. We're still investigating the best database and query engines for engineering applications, but it does show the direction of our roadmap. Today, Syndeia is MBSE-centric. That is, it's usable by systems engineers with SysML tools at their disposal. But this kind of system information is potentially important to every engineer and every engineering manager in the organization, and it needs to be accessible in multiple tools and portals as an enterprise application for model-based engineering. The next planned release, Syndeia 3.2, moves us in that direction. It will be available as a standalone app as well as a SysML plugin, and it will begin to offer the ability to make direct connections between non-SysML tools, CAD to simulation, for example. More of the Syndeia functionality will be implemented as services, particularly in the visualization area, and very importantly, more customer flexibility in mapping between domains will be included. Well, currently, when we map model elements in one domain into another, transformation map is pretty much hard-coded, with only a few user-selectable options. This is a limitation for users who have customized their tools, creating new SysML stereotypes and PLM schemas. Syndeia will allow users more flexibility in choosing how information is transformed between domains, also how much. What elements and levels of the model are to be transferred, and which are to be protected. Syndeia 3.3 will move even farther into the enterprise domain, putting more functionality into services for local clients in any part of the toolchain, and putting more of the full power of graph database queries into easy-to-use form for exploring the total system model. So, to sum up, why should Syndeia be part of your MBSE solution? Well, first, we work with your current tools, and your future tools, and your partners' tools. We are vendor neutral. Second, we support your use cases. We are not pushing a particular approach to MBE. Some experts talk about a conflict between link and sync approaches in connecting models. Syndeia supports both. Third, Syndeia provides a consistent interface across many connection types and use cases. Some vendors supply point-to-point connections, and some users create their own, but there is a value to using the same database, the same dashboard, and the same drag-and-drop operations across multiple different kinds of connections. Well, finally, I hope I have shown that Intercax is offering a clear vision of model-based engineering. We've had the privilege of working with some of the leading-edge adopters of MBSE and MBE and helping them to implement real working solutions. Syndeia is part of that ongoing development, and we are sharing that with customers moving towards those goals. To learn more about Syndeia, our website has much more, including video demonstrations, and it's easy to get an evaluation license using the instructions that you will find there. Thank you for your attention, and let's move on into any questions.